The images on this disc are all diffraction patterns produced by passing visible light through narrow slits or small circular apertures and past other objects. This diagram shows in principle how plane waves, shown by wave fronts marking the position of the wave crests, are spread or diffracted as they travel through a gap in a barrier, emerging as spreading circular waves on the other side. If a second slit is opened adjacent to the first, the two diffracted waves interfere to produce a pattern of bright and dark fringes. The fringes are bright in regions where the crests of the overlapping waves coincide. At these points, the waves reinforce, producing constructive interference. The fringes are dark where crests of one diffracted wave coincide with troughs of the other. At these points, the waves cancel and the interference is destructive. In order to reproduce such diffraction effects with light, some care must be taken to use an appropriate light source. Natural white light consists of a mixture of all visible wavelengths, and the complex pattern of overlapping colours causes confusion. It helps if initial study of diffraction is restricted to the use of a source producing a single wavelength of light, called a monochromatic source. The red light from a helium neon laser is highly monochromatic and very effective. For many purposes, the yellow light from a sodium lamp is sufficiently monochromatic. The light illuminating the object must also be spatially coherent. In effect, this means that the same light wave must cover all parts of the diffracting object. The radiation from conventional light sources, including sodium lamps, comes from individual atoms at random. When these random emissions interfere, a very complex wave is formed, like the wave generated when a handful of gravel is thrown into water. In order to be coherent, the waves illuminating the diffracting object must all originate from the same part of the same source. Spatially coherent light can be obtained by using a pinhole or a thin slit to select light from just a small part of a conventional light source. A slit source is suitable for studying one-dimensional diffraction effects, for example from a pair of parallel slits or a diffraction grating. A pinhole source is needed to study diffraction in 2 dimensions, for example from a circular aperture or a 2-dimensional grid. A major consequence of using a slit or pinhole in this way is that only a tiny fraction of the total light output from the source is used. The resulting diffraction effects are not very bright and are usually viewed in darkened rooms. The nature of light generation in a laser is quite different from conventional sources. The photons emitted from individual atoms are all in step, so the light emerging from a laser is highly coherent, and a slit or pinhole filter is not required. We can use the whole of the light output and throw very bright diffraction patterns onto screens placed many meters away in only slightly darkened rooms. When a pinhole filter is used with a laser, it is for a different purpose. It is placed at the focus of a lens used to convert the narrow laser beam into an expanding beam. In this position, the pinhole filter blocks light scattered from little blemishes or particles of dust on the lens surface and has the effect of cleaning up the expanded beam without significantly reducing its brightness.